In this module, we will explore projectile motion. For constant acceleration in one dimension, there are two fundamental equations, the first giving position as a function of time, and the second, velocity as a function of time. In two or more dimensions, we simply replace the acceleration, velocity, and position with their vector equivalents. Now, you may recall that in addition to the two fundamental equations in one-dimensional motion with a constant acceleration, there were three additional equations we could derive by eliminating either the acceleration or the time or the initial velocity from the first pair of equations. Well, not surprisingly, we can do a similar thing for motion in two dimensions with a constant acceleration. If we eliminate either the acceleration or the initial velocity from the first two equations, the result is something which looks rather familiar. However, if we try to eliminate the time from the first two equations, the result is not that familiar looking. It involves something called the scalar product of two vectors, and this is something you may not have seen yet. It's also called the dot product. In any case, the result is an equation which for us right now is not nearly as useful as the other equations. And in general, it's always best to work from the two basic equations for position and velocity as a function of time. Let's assume we are given the acceleration, initial velocity, and initial positions. What does motion under a constant acceleration look like in two dimensions? Well, let's first consider the case where the acceleration vanishes. Let's assume we're given some initial velocity vector and some initial position vector. And now we want to consider the motion of some object, in this case, a small red dot. If we allow 1 second of time to pass, then the object will move in the direction of the initial velocity by a displacement equal to that initial velocity times 1 second. And the current position of the object after 1 second will be the vector sum of the initial position plus that velocity vector times 1 second. If we now allow another second to pass, it's going to move further along. And finally, 3 seconds, and we see the final position of the object after 3 seconds. What we notice is that when there is no acceleration, the particle moves along the direction of the initial velocity at a rate of the initial velocity, and the position simply increases from its initial position by a displacement given by the velocity times the time. Now let's consider what happens if we have a non-vanishing acceleration. All right, we allow a second to pass, and not only do we have a displacement due to the initial velocity, but we also get an additional vector displacement coming from the acceleration. And the final position is going to be given, again, by a vector sum of the initial position plus the displacement along the velocity vector plus the displacement along the acceleration vector. In this case, with a non-vanishing acceleration, the velocity itself is also going to change with time. And so after 1 second, the velocity is going to now point in a different direction. We can allow time to pass a little bit further, now going out to 2 seconds. We see again that the final position is the vector sum of the initial position plus the displacement along the initial velocity vector by the amount of time given, plus the displacement along the acceleration vector, multiplied by 1/2 times the time squared. And the velocity is also going to change further. And if we finally go to 3 seconds, we see the effect of both the initial velocity and the acceleration on the motion of the particle and on its velocity. What we notice is that the particle no longer travels in a straight line because there is a non-vanishing acceleration. What we notice is that the particle, which first moves in the direction of the initial velocity, well, as time passes, the direction of motion of the particle becomes more and more closely aligned with the direction of the acceleration. This is not surprising. If we look at the equation for the velocity as a function of time, we see that it is the initial velocity plus a times time. And as time gets later and later, as the time variable gets larger and larger, a times that time is going to get much, much larger in magnitude than v naught, and it will dominate. And so as time passes, the velocity will ultimately approach a direction very closely aligned with the acceleration. If we use Cartesian coordinates, we can easily rewrite the two vector equations in terms of their x and y components. So we notice that in the equations that have been written down, we had the vector equation, and next we rewrite each vector in terms of its x and y components. Now, if we collect all of the non-vanishing terms on the right and separate them into those multiplied by the I hat vector and those multiplied by the j hat vector, we see that the components of each, multiplying each unit vector, must vanish because on the left-hand side of the equation, the components vanish. And so what we see is that in terms of Cartesian coordinates, the equations for motion in the x and the y directions are simply copies of the one-dimensional motion under constant acceleration. We can do the same split for the velocity equation, get the same result. Now, we can choose to orient our Cartesian coordinate axes so that one of them points in the direction of the acceleration. The component of the acceleration in the other direction will then, of course, vanish. So let's, in this case, choose our acceleration to point in the same direction as the y-axis. In this case, the x component of the acceleration vanishes, and our equations simplify considerably. Now, in problems with constant acceleration, the direction of the acceleration, it's special. Objects will accelerate in that direction, and both the positions and velocities will change with time in that direction. On the other hand, in the direction perpendicular to the acceleration, there will be no acceleration. The velocities perpendicular to A will remain constant, and only the object's positions will change. Writing the equations for position and velocity in terms of Cartesian components allows us to see this independence of the parallel and perpendicular motions explicitly. The equations for x and y motion decouple. Now, this is not going to be true if you don't use Cartesian components. The decoupling, well, I shouldn't say decoupling, the independence of motion parallel to the acceleration direction and perpendicular to the acceleration direction is true in general, but we can only see this in terms of the equations if we use Cartesian components. A very common example of 2D motion under constant acceleration is the motion of an object under the influence of gravity with air resistance assumed to be negligible. Using Cartesian coordinates, we orient one of the axes in the direction of gravity, that is vertically, and the horizontal axis can be placed in the plane formed by the vertical direction and the direction of the initial velocity. So even in more than 2 dimensions, we can reduce every problem down to motion in 2 dimensions by aligning our coordinates in the plane formed by the vertical direction and the direction of the initial velocity. Now, keep in mind that if the initial velocity happens to be vertically directed, then we have actually only one-dimensional motion. But in general, it will always be, or it will be 2-dimensional motion. All right, so for projectile motion, the basic equations are just the y position as a function of time, the velocity in the y direction as a function of time. Both of these involve the gravitational acceleration. And finally, the x position as a function of time, which only depends on the initial velocity and the initial position. Let's assume we have some particle and we know its initial position x naught and y naught. Let's further assume we know its initial velocity in the x direction and its initial velocity in the y direction. With this information, we have enough information to know the full trajectory of the particle as a function of time. So initially, if we put in t equals 0, we just get back the identities that the initial y position is y0, and so forth. Now, if we let time pass, and we go to some new time, t1, well, the y position of the particle will be given by plugging t1 into our equation for y position and expanding. And we can do the same thing for the y velocity, the x position, and the x velocity. Of course, the x velocity is going to remain a constant. We can go to some later time and do the exact same thing, but the second time that we're considering is actually a very special point in time. I've chosen this to be the point in the trajectory where the particle has reached its maximum height. At this point, the y velocity is going to vanish because first the velocity is up. At this point, it goes to 0, and then later in the trajectory, the y velocity will be negative. But the y velocity goes through 0 at the top of a particle's trajectory. So, the equation for the y velocity, assuming we know the initial y velocity, is enough to tell us the time at which we reach this maximum height in the trajectory. We wait a little time further, and now the particle is coming back down. We can again plug in time t3 during this point in time after the particle has reached its maximum velocity, and we can calculate the positions and velocities of the particle. And now we go to what will be the end of this particular trajectory, where we reach back to the same y position we started with. We start at ground level and we return to ground level. This is again a very special position in the trajectory. It doesn't always happen for every problem, but for this example, we're letting this happen. Because we know we have returned to the same height, y0, we can use the equation for the y position as a function of time to determine the time t4 at which the object will return to ground level. That equation will actually have two solutions, one of which is t equals 0, but the non-zero solution, t4, will give you the time of flight of the projectile if it is traveling from one particular level up in height and back to its original starting height. Now, if we take that time t4 and plug it into our equation for the y velocity, in this particular special case, we're going to find that the final y velocity here has the same magnitude as the initial y velocity, but the opposite direction. Again, I want to emphasize that this is only because we have the particle returning to the same height. If it's at a higher height or a lower height, the velocities will be different. So let's consider this very special case one more time. When we return to the same height, we can use the equation for the y position as a function of time to determine the time of flight of a projectile. We can use the equation for the velocity as a function of time to get the time at which we reach the maximum height in the trajectory. And we can use the time of flight that we calculated first in the equation for x position as a function of time to tell us how far in the horizontal direction the projectile has traveled. This is called oftentimes the range of the projectile motion. And for this special case, we also have the fact that the time at which we reach the highest point in the trajectory is exactly halfway through the trajectory flight all the way back to the original altitude. Now, what we just looked at is the simplest possible example of projectile motion. We know the initial position and the initial velocity. We can then determine the position and velocity at any other time. But what if we don't know one or more of the four pieces of information given in the initial position and the initial velocity? Well, in that case, we must replace each missing piece of information with some new piece of information. And as a rule of thumb, what you can do is think of it in the following way. Look at this tableau where the first line involves the quantities in the X motion, and the second line, or the last line, the motion in the Y direction. And in the middle line, we have time, which is the parameter which links together the X and the Y motion. If we're missing some piece of information from the initial positions or the initial velocities, then we must replace each missing piece of information with some new piece of information from the same line, but at some specified time later in the trajectory after the initial conditions. So this is just a sort of rule of thumb for how to solve problems. You'll get more understanding of how to solve projectile motion problems by getting some practice with some example problems.